So I'd like to introduce Amartya Shekhar Dubey from the National Institute of Science, Education and Research in India. Thanks.
So I'd like to thank the organizers for organizing an event like this, like annually, something that I really look forward to like every time. So it's great, it's great even for like young people like us, and it's overall a great experience. Right? So I also gave a talk last time actually. It was good. So so I'll be talking about EN algebras in m+1 categories. So as you can see, this is joint work in progress with Leon Liu from Harvard. And let's begin. So, a warning. So I have a sore throat. So if in any case you don't hear me or you don't understand what I mean, so feel free to like just stop me. Sorry in advance. Right. So here's the plan. So I'll start with some bit of an introduction, then moving on to the motivations. Then I'll talk about the E1 case, like the way we think about E1 algebras in an M category. And then I'll actually, for the E2 case, I'll try to do something on my tablet. I'll try to show how to think about it. How to think about attacking the problem, how we thought about it. So I'll try to do something on my tablet, but we'll see. And then I'll state the main theorem and sketch a proof. So I'll try to keep it a bit intuitive and a bit short, considering the time frame that I have. So I'll not go through all the details, right? So let's begin. Okay, so an M category means an M1 category in the typical notation that we have. So let's recall what an M1 category is. A category C is an M+1 category if the Ham set is M truncated for any two objects, right? So the set of morphisms that you have. So there's untruncated. Excuse me. Right. So for M greater than or equal to -1, a space X is M truncated if you take all the homotopy groups, like of X, of course with some base point, and they vanish for I greater than or equal to M, right? This M that we have here. So for M being equal to -2, that basically means that it is contractible. So it is too truncated if it is contractible. Right. So an example is just an ordinary category. So that is an 1 category, and the category of n-truncated spaces, that is an n+1 category. So moving on. So some motivation. So by the way, I'm sorry. Do you see my titles or should I move this somewhere? I don't know. I myself don't see my titles. It's all good. Okay, sure. Let's continue. So for ordinary categories, there's a rich theory of monoidal braided monoidal or symmetric monoidal structures. So the goal is to extend this to higher categories. While we already know that the homotopy generalization of these monoidal structures are EN operands and their algebras. So at this point, there's no explicit data, right? For example, the notion of braided monoidal algebras for higher categories. So that's an example, right? So the question in this talk, the question that we address is, how do we think of constructing EN algebras in m+1 categories? So, before moving further, so kind of set the stage by a few definitions, just to recall a few definitions. Right? So what I mean by a map of operands to be n-connected. So just a few definitions, just to recall a few things, right, before moving on. Right, so here's what I mean by a map of operands to be n-connected. Right? And so similarly, when do we say a map of operands? It's n-truncated. I don't know. I think I'll have to get rid of this. Okay. So similarly, we have it for a map being n-truncated if this map is n-truncated, right? So again, so always an m+1 operand if this map that you have is n-truncated. Right? So So that's the definition that we use. So now, so a couple of important results. So if you have a symmetric monodal infinity category, right, C, then the C tends to like the if this is the underlying category of this operator, then this is an m+1 operator if and only if C is an m+1 category. So these are like really all of them are like really well-known results. So just recap. So another result, like if this is like an untruncated map and C is a symmetric monodal m+1 categories, so this is an equivalence. Let me make sure everything's right. Yeah, cool. Right. So yeah, so moving on to the E1 case. So E1 algebras, that is something that we all know well. So yeah. So it turns out we already have an answer to James Tashev. So we have this filtration. So I'll try to go through this section a bit fast because we know this well. So basically moving from AN to n+1, we fill in a KN cell. And then the higher self units. So that's the basic idea. And right. So importantly now, so this AN to AN+1, the map that you have, that is n-3 connected, and yeah, this is very important, as we'll see. So okay, oops, there's a typo. So it's supposed to be bold A, not a mathematical. Right. So right. So this implies. Oh man. I'm sorry again. I don't know. I don't know how to get rid of this. This is obstructing my view. So really appreciate if someone can like, maybe help me with this.
It looks all fine on our end.
Okay, so there's no obstruction for the bottom part. Okay,
Yeah.
it's just for me. Okay, cool. Works. So okay, so this implies this. So that basically gives us what we want, right? Again, there's a typo. I'm sorry, this is supposed to be. So C is not a subscript. So it's the E1 algebra of C, where C is an m+1 category. It's the same as the AN+1 algebra. Right. So E1 is basically just A infinity. Right? Okay, so right. So for E2 algebras, okay, so I'll grab my pen and try to do things on my tablet right now. So oops. Right. So I'm again, I apologize for my bad handwriting. Just I've gotten used to writing on boards these days. So writing on tablets is just kind of bad. Right. So what are E2 algebras in M categories? Right. So now so we know that E2 is just like E1 times 1. Right. So what we want is like, so we'll get the E2 by, so we have a diagram of this form, right? We have something of this form, and we'll get E2 by filling in each cell. We have a filtration of this form. So we'll get E2 by filling in these, right? So now, so we try to do the most stupid thing, like the simplest thing, that is the cell counting, right? So right, so cell count. So again, so this is like so this at the end we get that each cell is K1 plus K2 minus 4 connected, right? So this is just like right. So these dots are basically like I don't know. Let me try and draw this for you. So right. So we want to fill in the cell relative to these, right? Relative to the left and bottom. So we have something like this K1. So by these dots that we have, oops, sorry, there seems to be something wrong with the pencil. Okay, that's wrong, and I'm glad that I think there seems to be something wrong with this, but yeah, the point is that so this is just this is just K1. So first, this is damn. Sorry. So this okay. So this is like AK1 tensor AK2 plus 1. This is like AK1 tensor AK2, and this is AK1 plus 1 tensor AK2, and this is our K1 plus 1 tensor AK2 plus 1. So this is what I wanted to say basically. Right. So okay. Again, there seems to be something wrong. Oh, apologies for that. Okay, right. So now by the classical Eckmann-Hilton argument, if we take the unitable binary operations like star and plus that I say, and you have something like this again. I apologize for my handwriting. Then you have the fact that they're the same, then they're associative and commutative. So basically the idea is that yeah, so basically the idea is that this we'll get the one categorical things. So we have these triangles, right? You have these triangles. Okay, now it works. We have these triangles that'll give us the like one category, the cases for one category, two category, and stuff like that. Right. So now using this Eckmann-Hilton argument, so what we can do now is like by plugging in units, and by a bit more work okay, let me try and explain this. So right, by plugging on the units, so suppose so by plugging on the units, you'll get something like this. So you should have this in your mind. Again, I'm not sure if my pencil will work, but let me try to run this a bit fast. So the thing is that the point is that this triangle will give us the case for one category is like EM algebras and E2 algebras in one categories. This triangle will give us like two categories, like so this is now we'll see that by the Eckmann-Hilton argument we'll get simplifications. We'll get like by these plugging in the units here. So you'll get stuff like this. So let me try and see if I can draw this. Okay, I'll try to. So the point is that, okay, let me try to say it. So the point is that you have you get a kind of stairs. So you get stairs like here to here, like you get a stairs like this, and you can literally climb onto these stairs to get the E2 algebras, right? So for instance, like yeah, I'm not sure. I have a slide for that. So that is the basic idea actually, and you try to find let me go through this again. So by the Eckmann-Hilton argument, we'll see we can plug in the units and we'll get a simplification such that so in order to get the E2 algebras, we'll get something like a staircase like this, right? I hope you can see my picture, right? So we'll get something of this sort, and that will actually give us our answer. So let me get back to my slides right now. I have a slide for that, right? Right. So okay, here's the generalization. So here's the generalized. So this is the generalized theorem. So by a bit more work, so the way we did it for the E2 case, we can similarly like have this like this. So this is like hugging the diagonal. So both of us like call it like hugging the diagonal phenomenon, right? But so it like hugs the diagonal, and you get a staircase of the form. So in the 2 case, for example, in the E2 case, you get a staircase, and in the third, like E3 case, like you get a higher dimensional analog. So you can generalize it, get this. Right? So this is the main theorem. And so here are, so these are the important consequences that we have. So I'll let you look at it for a second. All right. So this is 2k minus 1 minus 3 connected when k1 is less than k2 minus 1, and k1 plus k2 minus 4 connected when k1 is greater than k2 minus 1. And for a d plus 1 category, each algebras are equivalent. So this is like a corollary. Right. So as promised, so here's the table that I said, like, so let me kind of move on back to the diagram that I had. Let me try to do that so that I can kind of see things in perspective. Right. Right. So here, comparing it, so for the one thing you have 2 and 2, so that is like, just moving on. So there's this, you think of having a staircase. So this is 2, 2. So this will be the one case. Then you move on here. So that will give you 2, 3 for the 2 categorical case, and 3, 3, and so on. Right. So you get the idea. Right. So we see that. So that's basically the generalization. So we see that when we go from M category to M+1 categories, we increase one of the K1 while hugging the diagonal. So this also gives us a way to explicitly construct each algebras by filling in the appropriate Stashev associated heat log, right? So furthermore, all this generalizes to L, right? So that is the point. So here's a sketch of the proof. So we first begin by defining K-restricted operands. So there are 2 ways of you do it. So one is the classical way, Lurie does it, and another is the dendrital way of it, defining it as a sequence-free sheaf. Right? So this basically means this omega. This basically means trees with values less than or equal to k. Right. So these are the 2 definitions that you have. So that's right. So now we have this functor, right? So this has a left adjoint that you can roughly define as follows. So this is the way you think about it. So this is basically it's like all the ways to construct k morphisms from the less than k morphisms. That is the left adjoint that you have. And cool. So it turns out there's a problem with the right adjoint. So it doesn't exist all the time. So we have a right adjoint only when you restrict it. So that's one of the few subtleties that we have in this generalization of the Eckmann-Hilton Argument. Right? So you have a right adjoint when restricted to unital operands. So that you can again roughly define as follows. So just by plugging in the units. So generally, like you can do a few cases and stuff like that, but more generally, so for symmetric monolith unital infinity category with elements, you have something like this. It's the way you think about the right adjoint. Right? So for a lot of notations, I can just maybe stare at it for a second. That makes sense, right? So where this F, so that is basically this Q that we have. So let me get back there. So that is, excuse me. So right. So here's the theorem. So if it is D1 connected, you have a map of operands and this like restricted version. Okay, restricted version, so it is an equivalence. And R is D2 connected, then this map is a D1 plus K times D2 minus 2 connected. So right, so here's the proposition. So if R is D connected, right? Is D connected, coherent, then so this is basically an ingredient for proving this theorem. So that basically would prove the general case, right? So just stated here. So it's important to note that operas in N are coherent, but these ANs are not. So that is a big thing for proof, right? So yeah, I don't have more to say. So maybe I can try to go back to the notes that I have and try to draw these stairs or something like that. Still something seems to be wrong, but I'll just try and draw the ladders. Really sorry, like there seems to be something wrong. There seems to be something wrong. So again, like yeah, like maybe look at it again. So I'll try and not use my pencil. So let's look at the E2 case again. Let's try to look at it again. So how you're trying to fill it using fill in KNs, right? So this is basically right. So yeah, let me try and work with this typo. So so this will give us the one. So this triangle will give us the one category. The E2 algebras in one categories again. That has to do with the Eckmann-Hilton, classical Eckmann-Hilton. And this diagram will give us for two categories, and turns out like you'll get a stair like this. So this is A2 tensor A2. We'll get like for two categories, you'll get A2 tensor A3. Then you'll get for three categories, you'll get like A3 tensor A3 and so on. And you have right. So yeah, I wanted to say that again. Just make that up. Right. And for the general case, right. So this is basically what I'm listing in the table. Right. So this right. So this basically gives us a way to explicitly construct E2 algebras by filling in the appropriate associahedron. Like yeah, and this furthermore generalizes to EL. So also you have like more complex filtrations, like different and you get like EL to be like the colimit of those like diagrams that you'll get. Like in the E3 case, you'll get cube or stuff like that. So okay, maybe because I'm done, let me say let me add a few remarks. So like as I mentioned, like things that like a few important things like that I mentioned, the things that are kind of difficult, that were kind of difficult, are again the stuff that I mentioned about the right adjunct, like explicitly constructing the right adjunct. That is something that is a bit subtle, right? And actually, still, it's kind of mysterious. Like to be honest, it's still kind of mysterious. This happens, but yeah, that was a big step, and right. So maybe for as a reference, I don't know, for the Eckmann-Hilton argument, that is something that like we've like explicitly used in like most of us. So that is the paper by Shankianovsky. That is I think the title is Infinity Categorical Eckmann-Hilton Argument. So it's like an extension of that argument. So that was one part. So that is one comment, and the second comment is this fact that I added, like this coherence issues, right? So that has been also been something that has been like kind of a challenge, but yeah, there's a lot of things that I probably did not mention. I think I undertimed myself, but I think that's good. So we have most of the discussion. So right, I'd like to stop here and thank everyone for listening.
Thanks very much. Let's thank the speaker. Okay, thanks very much. Any questions from the audience?
Simon has a question.
Simon.
Hi, yes, very interesting. So I'm kind of curious if you have a way to simplify a little bit those n-fold tensor product of A and operad, in the sense that it's still going to be like a lot of operation, like AK itself is just basically K different operation in various dimensions. But if you take a tensor product of a certain number of them, you're going to get like K to the nth power operation. So it's still a lot compared to what you would expect for like a minimal model of the EN operad. So do you have a way to kind of simplify that?
Well, so yeah, I think we're not sure about it, like whether like this is like a minimal construction or but I don't know.
Yeah, sorry. Maybe I can try it for a little bit. So
yeah,
so let's do an explicit case. So let's do the case of gradient monoidalness for one categories. So there you're looking at our theorem tells you it's A2 tensor A3, and then it's kind of what you were saying, what you actually might expect, what you have to write down association to fill in after you're giving A2 tensor A2, so just two commuting operation. It's a 6-string. It's a diagram where you have to permute 6 elements. And interesting enough, what it's actually doing is the ends of those 6 strings are fixed. What happens is that in the middle 4, you're actually doing you're doing one random master and you're doing the inverse too. So it's actually a 6-string element that encodes both of the classical hexagon axioms.
Yeah, it's useful if you draw diagrams like in terms of these random masters, but unfortunately my pencil doesn't work.
Yeah,
that's a way to see it, right?
Yeah, so you see right away it's equivalent to the Brady-Monado thing, but it is different. And you know, you have more strands, but it will package more identities at the same time. So that's one thing I want to say. And the other thing is that there's a paper recently that by one of Thomas' students that showed that like to define an EN operad, you on an M category, you actually can only think about operation spaces less equal to M. So basically you just have to apply the identity to a bunch of them to get to. So that's how we can think about it. So you either do the 6-strand all by itself, or you plug in 3 identity and do each 3, and in which case, both of the case you see that you recover the 2 hexagon axioms.
Okay, if I can ask one more question.
Yes.
So if I'm understanding correctly, maybe I'm missing how the Bondman-Vogt tensor product works. But if I do a tensor product of like, I don't know, E2, A2 times E3 or more of those, I'm gonna get an operad where I have 2 different way of multiplying elements, right?
Yes.
But do you have a way to like remove one of those multiplication so that we only have one?
Yes. Great. That's a very good point. So basically, I don't think it's said in this presentation, it's kind of short, but there is this like this. So this is symmetry in E2 operad, which is rotation by 90 degrees. And that symmetry basically allows you to glue in, like you can fold it around the diagonal and glue it into the other end, right? So in that sense, when I go to A2 tensor A2, I'm not really introducing a new A2 structure. It's the same as my original multiplication. So it's exactly what you said. So there is a process there. It is not explicitly said in this formulation of the result. But yes, there is.
Yeah, I was about to add it.
Yeah,
I was about to add it, like, but as you saw, like pencil malfunctions. I was about to add it, like towards like in writing actually, but yeah. Thanks, Leon.
Okay, thanks.